Hello everyone, I am Durai Kannan. I have more than 30 years of experience in power electronics products development. I take this opportunity to share my experience to young engineers. I would like to present control system design techniques for power electronics applications. I tried my best to build it from basics within the constraint of keeping it to about 1.5 hours duration. I hope anyone from electrical engineering background will be able to follow. There is no need for trial and error. This presentation will provide a solid foundation for anyone engaged in control system design. This can also be a recap for someone who lost touch with the topic. Let me go to the technical presentation now. Let me start with a review of transfer function and Bode plot, which is essential for the control system design. A simple RC circuit is considered to explain the transfer function on Bode plot. The complex impedance of the capacitor is 1 over Sc, where C is the capacitance. Output voltage can be derived in terms of input voltage. Vi divided by R plus 1 over Ac is the current in the RC circuit. The current multiplied by 1 over Ac is the output voltage. So output voltage derived in terms of input voltage, this equation. Output voltage divided by input voltage is simplified to 1 over 1 plus ACR. Substituting j omega for S in this equation, we get VO by VI in terms of omega, the frequency in radians per second. So this is a complex number. The magnitude of this number is equal to 1 over square root of 1 plus omega CR whole square. In dB, the magnitude is given by this equation, 20 log magnitude here. The phase is minus tan inverse of imaginary part divided by real part, minus tan inverse of omega CR. Right side, the Bode plot has been shown. X-axis is frequency in hertz in logarithmic scale, and y-axis is dB in linear scale, and for the phase y-axis is in degrees. When omega is equal to 1 over RC, this term is 1, and when omega is much less than 1 over RC, this term will be much smaller than 1. So the magnitude will be 1, and in dB 20 log 1, that is equal to 0. So here the corner frequency is 1500 Hz here, and on frequencies, for frequencies much less than corner frequency, the magnitude is 0 dB here, and the omega is, if omega is more than 1 over RC, then this term will be much higher than 1, so we can neglect 1, and the magnitude become 1 over omega RC. Omega is in the denominator, so as the frequency increases, the magnitude will fall, and you can see that the magnitude is falling as the frequency increases. It falls 20 dB for decade of frequency. From 1 kHz to 10 kHz, it falls 20 dB, and from 10 kHz to 100 kHz, it falls another 20 dB, and so on. For the phase, when omega is equal to 1 over RC, this term is 1, minus tan inverse of 1 is equal to minus 45. So at the corner frequency, which is here 1500 Hz, the phase is 45, and the phase at frequency is much less than corner frequency, it is 0, and for frequencies much higher than corner frequency, it is minus 90. A better insight can be obtained by comparing frequency and time domain waveforms. For this purpose, I consider LCR circuit. The transfer function VO by VI is given here 1 over 1 plus SL by R plus S squared LC. By substituting j omega in the place of S, we are getting VO by VI in terms of frequency in radians per second. And here the final equations obtained by substituting values of L, C, R as given in the circuit. Here the corner frequency is 1 over square root of LC. In this case it is 3835 radians per second. In hertz, you will divide this by 2 pi, that is 610 hertz. When omega is 1 over root LC, this term will become minus 1, and 1 minus 1 then becomes 0, and only this term is left in the denominator. For high R, this value is very less, and then 1 over that value will be very high. So at square root of 1 over square root of LC, we can see a peaking in the magnitude plot. And the frequency is much less than the corner frequency 1 over root LC. The magnitude is 0 dB, and for after the corner frequency, the magnitude falls at 40 dB per decade because of this omega square term here. So here in this slide, both frequency domain waveform and the time domain waveforms have been given. It's the same LCR circuit with corner frequency 1 over square root of LC, 3835 radians per second, and 610 hertz. The magnitude and phase plot for different frequency has been given, repeated here. The right side we can see the time domain waveform. For frequency 200 hertz, the input and the outputs are given. Input is a sinusoidal waveform is the input. At 200 hertz, the gain is, you can see that here 0 dB, it's slightly more than 0 dB, so slightly more than 1. So when 200 hertz waveform is applied, that's in the red one, the output is the blue one, and you can see the magnitude is slightly more than the input, and the phase at 200 hertz is, again it is here is 0, so slightly less than 0, slightly lagging, and one can see that the waveform is slightly lagging the input voltage and magnitude is slightly higher. The input at 200 kilohertz is given here. This is the input waveform. The magnitude is 1 at 200 kilohertz. At 200 kilohertz, the magnitude here is, you can see it is minus 20 dB. It is about 0.1. So the magnitude of the output is 0.1. At 200 kilohertz, the phase is, you can see minus 180, close to minus 180. So we can see that output waveform, this is input waveform, output waveforms inverted. The transfer function, if it is expressed in poles and zeros form as given here, it's much easier to understand and analyze. The denominator, the omega P1, omega P2 are called poles, and in numerator omega Z1 and omega Z2 are zeros. Let us assume that omega p2 is much more than omega p1 and omega z1 is much more than omega p2 and frequency omega z2 is much more than omega z1. Okay. When the frequency, actual frequency is less than omega p1, it's going to be less than all omega p2, omega z1, omega z2. So all these terms will be negligible and effectively all 1 only will remain. So the magnitude will be 1 and 20 log 1 is 0 dB. When omega is equal to omega p1, so first corner frequency is reached. After crossing the corner frequency, the 1 will be negligible and this will be appreciable magnitude. So the magnitude will be falling at 20 dB per decade. And since all these omega p2, omega z1, omega z2 are higher frequencies, still the effective magnitude of these terms will be 1. So when frequency reaches omega p2, this pole will become dominant. So already there is a minus 20 dB per decade due to this pole. And here after crossing this omega p2, there is another 20 dB per decade fall of magnitude will be happening. So totally after crossing omega p2, the magnitude will fall at 40 dB per decade. When omega reaches omega z1, after crossing omega z1, since it's a numerator, the magnitude will increase at 20 dB per decade. So 40 dB per decade when added to the increase of 20 dB per decade, so net fall will be at 20 dB per decade. After crossing omega z2, another 0 at omega z2, when the frequency crosses omega z2, there is another 20 dB per decade increase in the magnitude. So 20 dB per decade fall, again after omega p2 40 dB per decade fall, after omega z1 20 dB decade fall, after omega z2 it is flat, magnitude will be constant afterwards. Regarding the phase, when omega reaches omega p1, since omega is far less than all other poles and zeros, the phase will be 45, and when it reaches omega p2, this already would have become already minus 90 and another 45 will be added, so minus 135, and when omega reaches omega z1, there will be plus 45, so it will become again 90 minus 90 minus 90 plus 45, it's about minus 145, and when omega reaches omega z2, minus 90 plus 90, so net minus 90, and this provides plus 45, so it will be minus 45, and as frequency is far higher than omega z2, it will become 0. So this transfer function is taken as an example and explained here. You can see the first pole is 62.83 radians per second. Second pole is 10 times this, and first 0 is 10 times the second pole, and the second 0 is 10 times the first 0. 62.83 radians per second in frequency, if you divide by 2 pi, it will be 10 Hz, and this one corresponds to 100 Hz, and this 0 corresponds to 1 kilohertz, and finally this 0 corresponds to 10 kilohertz. When the frequency reaches 62.83, that is 10 Hz, after it crosses, the magnitude should fall 20 dB per decade, because the magnitude for all these things will be 1, and here it will start falling at 20 dB per decade. At 10 Hz, you can see the magnitude, it starts falling 20 dB per decade. After it crosses 628.3, that is 100 Hz, another pole is crossed. So the magnitude fall at 40 dB per decade. And when it crosses, when the frequency crosses 6283, that is 1 kilohertz, now this being 0, there will be a 20 dB per decade. Magnitude will be increasing. So the net slope will be from minus 40 dB per decade, it will become 20 dB per decade, minus 20 dB per decade. After crossing this 0, another 20 dB per decade, magnitude will increase, so the net constant magnitude. Similarly, for the phase, when 62.83 actual frequency reaches 62.83 radians per second or 10 Hz, the phase will be 45. Here is the phase shown here, it is 45, approximately 45. When the omega reaches 628.3, that is 100 Hz, already this has become minus 90, and this adds another minus 45, so minus 135. 100 kilohertz, the phase will be minus 135. And when omega reaches 6283, and we had minus 90 here, this has become minus 90, and here it will be plus 45, so it will become minus 145 at 1 kilohertz. It's about minus 145, and when the omega reaches the second 0, and we have minus 90, plus 90, minus plus 45 here, so it will be minus 45 net, and you can see that it will be about minus 45. I have taken the example of low pass filter again to explain the Bode plot. So this is this implementation is using an operational amplifier. This is the input and this is the output voltage, and with just R1 R2 without C2, it's just a negative gain amplifier with the amplification of R2 by R1. With adding C2, it adds filtering as well. It became a first order filter, and minus VO by VI is given by R2 by R1 multiplied by 1 plus S R2 C2. It's minus because it's a negative gain amplifier. Here the Bode plot of this transfer function is shown here. So the corner frequency is 1 over R2 C2. When S, the omega is much less than 1 over R2 C2, this term will be negligible, so the gain is R2 by R1. In dB, it's 20 log R2 by R1. That's the gain. After crossing 1 over R2 C2, the gain, the magnitude falls at 20 dB per decade. At 1 over R1 C2, the magnitude will become 0 dB. You can substitute and check it. As you can see that till the corner frequency, your input voltage is passes to the output without any attenuation, and beyond 1 over R2 C2, output voltage will be attenuated. So to filter a waveform above 1 over R2 C2, the first order filter is used. Now with this knowledge, let us go to the feedback control. Here there is an LCR circuit, and the capacitor voltage is fed back, and this is the reference voltage applied to the sum terminal. So the reference voltage minus the feedback capacitor voltage is the error voltage which is applied to the LCR circuit. The idea is that the capacitor voltage should follow the input voltage with a negative feedback. So here the same feedback control, negative feedback control is shown here, and a control block diagram is shown here on the left side. So we can derive the closed loop transfer function VOS by VIS. VOS by VIS is given by G of S divided by 1 plus G of S H of S. G of S divided by 1 plus G of S H of S. The G of S H of S is called open loop transfer function. Note that when G of S H of S magnitude is 1 and phase is minus 190. So here the magnitude is 1 and phase is minus 180. The denominator will become 0 and then magnet VO by VI become infinite. That means the system is unstable at the frequency when the magnitude will become 1 and phase is minus 180. So this happens when the phase at the zero crossover frequency in the Bode plot is 180. At zero crossover frequency, the magnitude is 0 dB, and if the phase is 180, in the open loop transfer function G of S H of S plot, then the system, the closed loop system, is unstable. So the stability analysis is done with the Bode plot of open loop transfer function. So the closed loop transfer function of the RLC circuit is shown here. This is the open loop transfer function, and VO by VIS, the closed loop transfer function, is given. So this is the open loop transfer function. This is VO by V error. That is, this is the transfer function of the LCR circuit, which already we have shown. And the closed loop transfer function VO by VI is given by, as mentioned earlier, G of S divided by 1 plus G of S H of S, which is 1 over 2 plus 1 S by LR plus S square by LC. So this is the Bode plot of RLC with open loop, which we already seen. We've seen that at frequency, resonant frequency 1 over root LC, then there is a peaking, and 0 dB at lesser frequencies and 40 dB per decade drop in the magnitude at higher frequencies, and around the corner frequency the phase varies from 0 degree to 180 degree, minus 180 degree. And here the Bode plot of RLC with closed loop is shown here, and closed loop transfer function, just the previous slide was derived. The magnitude peaks at 860 Hz, that is at 0 dB crossover frequency of open loop. As mentioned in the for the stability, it was mentioned earlier that at 0 dB crossover frequency, if the phase is close to 180, then the output magnitude will be very high. Peak magnitude depends on the phase at 0 dB crossover frequency in open loop. Phase at 0 dB crossover frequency in open loop plot at 860 Hz is 164 degree, very close to 180 degree. So the gain margin, phase margin and bandwidth are obtained from Bode plot of the open loop transfer function. This is the magnitude plot. The magnitude crosses 0 dB at this frequency, that is 61 Hz. How far the phase is away from 180 degree at the 0 dB crossover frequency is the phase margin. Here the 0 dB crossover frequency is 61 Hz and the phase at 61 Hz is minus 136. So that is 44 degree away from 180 degree. So 44 degree is the phase margin. In the phase plot, at this frequency the phase is 180 degree, that is 242 Hz. At 180 degree phase, how far the magnitude is away from 0 dB? 0 dB is here. That is the gain margin. It is 22 dB here. So the 0 crossover frequency or bandwidth is 61 Hz. So the 0 dB crossover frequency is 61 Hz here. That is the bandwidth of the control system. The higher the bandwidth, the faster the control system response will be. If the magnitude plot crosses 0 dB at say kind of 1 kHz, the response will be much faster than when it crosses at 61 Hz. Now let us see the feedback control again, and with a compensator here. The compensator output is applied to LCR circuit and the capacitor voltage is fed back. This is the reference voltage. As mentioned earlier, the idea is to capacitor voltage, to make the capacitor voltage follow the reference voltage. So in the control block diagram, we come to V feedback. We know that it is same as the LCR transfer function. We call it as a plant, and this is a compensator. The compensator transfer function comes here. The error goes to the compensator, and V reference minus V feedback is the error. So this is the control block diagram. Now the objective is to design a compensator such that V feedback follows the V reference without oscillation, and it has to follow as closely as possible. Steady state error is another important parameter of control systems. Here a control system circuit has been shown and its block diagram has been shown here. In this circuit, there is a reference voltage and the capacitor voltage is the feedback voltage. The capacitor voltage is subtracted from the reference voltage, and that's the error. The error is applied to the LCR circuit, and that produces a steady state capacitor voltage. The idea is that the capacitor voltage should be equal to reference voltage at the steady state. This is the control system block diagram. reference voltage, feedback voltage, and error multiplied by a transfer function is the output voltage. Output voltage multiplied by another transfer function is the feedback voltage. Generally, the H of S is nothing but a filter. Output voltage is filtered and given as a feedback. Sometimes gain also be given. The closed loop transfer function, that's equal to VOS divided by VIS is equal to G of S divided by 1 plus G of S H of S. For H of S is equal to 1, VOS divided by VIS is equal to G of S divided by 1 plus G of S. Then H of S is equal to 1. At steady state, VO is approximately equal to VI when the DC gain of G of S is far greater than 1. That means the DC gain of G of S is far greater than 1. So the 1 is negligible. So this will become G of S by G of S, that is equal to 1. The V error here is VO divided by G of S. So if G of S is much larger than 1, that means for the DC gain of G of S is very high, we can see that VO divided by the DC gain, which is VR, will be very low. So that is the difference between reference voltage and the feedback voltage. So the feedback will be closely following the reference voltage. For integral control, VA will be exactly equal to VFB at the steady state. VO is equal to VFB divided by DC gain of H of S. VO multiplied by the DC gain is the VFB. So VFB divided by the DC gain will be VO. For example, if H of S DC gain is half and the input voltage is 2, the feedback will be 2 and the output voltage will be 2 divided by half is equal to 4, or 4 multiplied by half is equal to 2 here. So this gain is used to get various output voltage for given reference voltage. The steady state error can better be explained in a PI controller. Here is an implementation of PI controller using an operation amplifier. At the positive terminal of the operation amplifier, we are applying 2 volts DC. We all know that the voltage at the negative terminal will be equal to positive terminal. That's 2 volts. If there is a difference here, because of the high gain of the operation amplifier, high open loop gain of the operation amplifier, the output voltage will not be in active region. It will be in saturation, either positive maximum, power supply maximum, or negative power supply maximum. So in the active region, the negative input voltage will be 2 volts. Supposing that VI is more than 2 volts, then a current flows into R1, that is given by VI minus 2 divided by R1. Because the operational amplifier input impedance is very high, all the current will go into this circuit with R2 and C2. As this current flows in this direction, you can see that capacitor voltage will be increasing, assuming the dot terminal is positive. The output voltage is 2 minus resistance voltage and the capacitor voltage. So as the capacitor voltage increases, output voltage will decrease. Supposing there is a system, as VO decreases, VI also decreases. So we started with VI greater than 2 volts, the reference voltage. So the VI decreases. The current through R1 and then current through R2 and C2 will stop only when VI is equal to reference voltage V2. That is the same voltage at negative input terminal. That is when the steady state is reached. The VO will settle at the voltage when VI is equal to 2. As there won't be any more changes in these voltages, and this voltage is fixed voltage. So the VI is exactly following the reference voltage. In this case is 2 volts. The steady state error is equal to 0 here. Let us see some controllers before designing a control system. A PI controller is very widely used controller, so we start with this first. An implementation of PI controller with operational amplifier has been shown here. One can readily obtain the transfer function, that is VO divided by VI here is given by K multiplied by 1 plus ST1 divided by ST1. So K is a proportional constant, and one can see that there is a 0 at S is 1 over T1, and there is a S term in the denominator, that means a pole at the origin. The 0 is the proportional gain is R2 by R1, and then the 0 is at R2 C2. After C2 there is a 0 and the gain is R2 by R1. Let's see the Bode plot of this in the next slide. So the transfer function is repeated here. Kp multiplied by 1 plus S by omega b divided by S by omega b. So when S is equal to omega b, there is a 0 and there is a pole at the origin. Okay. So when S is much less than, the frequency is much less than omega b, this term is negligible. So GS will be Kp divided by 1 over S by omega b. So there is only S term is there, which is nothing but j omega. So the phase will be minus 90 and the magnitude will be, as omega is in the denominator, it will be falling at 20 dB per decade from origin. When omega reaches omega b and cross this term will be less, so we can neglect it. Then effectively S by omega b divided by S by omega b, this will become 1. So GS will be Kp. So after the crossover frequency, here it is 100 Hz. So it become the magnitude will be Kp. Since the Kp we have taken as 10 here, 20 log 10 will be 20 dB here. And as initially there will be a J term, this will be negligible. 1 over S by omega b, there is a J term in the denominator, so minus 90 degree. After omega, frequency crosses omega b, so this term is negligible, so this this cancels and let Kp. So magnitude, the phase is 0. This is another popular compensator. It's called type 2 compensator. Again, an implementation using operation amplifier has been shown here. So the type 2 compensator simplified transfer function is shown here, where C1 is far greater than C3. When C1 is far greater than C3, this is the transfer function of the type 2 compensator. And here you can see a pole at origin and another pole at R2 C3, and then a 0 at R2, 1 over R2 C1. A pole at origin, another pole at 1 over R2 C3, and a 0 at 1 over R2 C1. Okay. Since there is a pole at origin, the Bode plot, the magnitude, it falls at 20 dB per decade from the origin. So generally this 0 comes next. When omega crosses 1 over R2 C1, this 1 will be negligible. So net will be again here still at a higher frequency. So this here also will be 1. So we have C1 cancels. It will be R2 C1 cancels. So the gain will be R2 by R1. So after the crossing 0, 1 over R2 C1, so we have a flat gain of R2 by R1, 20 log R2 by R1 in dB. When omega crosses 1 over R2 C3, there is another pole effective, then the magnitude falls at 20 dB per decade afterwards. So the only difference between type 2 compensator and the PI controller is that PI controller had a pole at the origin, and then there is 0, and from 0 onwards the constant voltage, constant magnitude. And type 2 compensator has got another pole. It's generally used for the filtering purpose. So another popular compensator is a type 3 compensator. Again, implementation shown using an operation amplifier, and a simplified transfer function of the type 3 compensator if C1 is far greater than C3. C1 is at least should be 10 times more than C3. This is the transfer function. Again, there is a pole at the origin here, and the first 0 will come at this 1 over R1 plus R3 C2, when omega is equal to 1 over R1 plus R3 C2. That is the first 0 comes here. 20 dB per decade from origin. When the first 0 cross, there will be a 20 dB per decade increase in magnitude, so that it become a constant. Then there is another 0 at 1 over R2 C1. So the magnitude increases by 20 dB per decade. Then we have a pole at R3 C2, 1 over R3 C2. So it will become flat. because there is 20 dB per decade, the pole causes decrease in magnitude by 20 dB per decade, so it becomes constant. Again, the last pole comes at 1 over R2C3. Again, there will be a 20 dB per decade fall in the magnitude here. Let's see how to use this type 3 compensator with an example later. So with this knowledge about the compensators, we can go to compensator design. Now this is our plant. LCR circuit is our plant. We have taken a very high R value. So with the very high R value, the damping will be less. So we have high peaking at the resonant frequency. That's 1 over root LC. And as we already seen, the magnitude will be 0 dB at frequencies far less than the corner frequency. And after the corner frequency, magnitude will fall at 40 dB per decade. The phase will be 0 at frequencies far less than the corner frequency. At the corner frequency, the phase will from 0 goes to minus 180. So these are the observations about the plant. Double pole near 0 dB frequency at 610 Hz. So we have a 0 dB frequency, 0 dB here. So there is a double pole near the 0 crossing. And 180 degree phase near 0 dB frequency. Again, the phase around 180 0 dB is about 180 degree. So magnitude 1, 0 dB and phase near 180 gives the low phase margin. So it's the closed loop system will be unstable without a compensator. Also at the DC, it's a 0 dB, gain is 1. That means the DC gain will be very less, lead to huge steady state error. Compensator objective. So we need a very high DC gain for good regulation. For the output to follow the input, we need a very high DC gain. With lesser DC gain, you will have a steady state error. Output will not be following the input. The above objective requires a pole in the origin. When there is a pole in the origin, the DC gain is infinite. So already we have 2 poles in the resonant at the resonant frequency. So this will lead to triple pole at resonant frequency. 1 pole from the origin, another 2 poles, 2 more poles at the resonant frequency. So we saw that near resonant frequency there is a 0 crossing, 0 dB crossing happening. So we need at least 2 zeros to be added so that around the resonant frequency for stability point of view. For a good phase margin, the magnitude plot should cross 0 dB with single slope. So that is 20 dB per decade. So with 3 poles near the resonant frequency, if you add 2 zeros, then effectively there will be 1 pole. That means the 0 dB frequency will be crossed at 20 dB per decade. Frequency crosses 0 dB at 20 dB per decade. So that's the criteria for the stability. The resonant frequency is 600 Hz. The compensator selection. Requirement from the compensator is pole at the origin for 0 steady state error.
two zeros around resonant frequency for good phase margin, gain margin, which just we saw. Both of the above objectives can be achieved by using a type 3 compensator. So we have a pole, the origin, the type 3 compensator. There is a two zeros here. This can be placed around the resonant frequency, and then two poles after that, much after the resonant frequency, should help make the system stable. Now let us go into the compensator design. The omega plant, that is the resonant frequency, is 1 over root LC, given us 3892 radians per second. For C1 far greater than C3, that this transfer function applies. The first zero, this is the first zero, 1 over R1 plus R2 multiplied by C2. So that is kept at 1/5 of the resonant frequency. We wanted to have two zeros around the resonant frequency to make the frequency cross the 0 dB at 20 dB per decade. So we have two zeros here. So one zero is kept at omega plant divided by 5 at frequency omega plant divided by 5. And again zero, another zero is 1 over R2 C1. And that is kept exactly at the resonant frequency. And also the gain at omega is at 1. See, that is this the flat region. So we wanted to have 20 dB at this after crossing the first zero. Then omega p0, there are two poles here, one at 1 over R3C2, another is 1 over R2C3. So these poles kept far away from resonant frequency. So they will be effective only after the frequency crosses 0 dB. So the frequency crosses 0 dB with single pole, then the two more poles added after crossing, and this makes the control system stable. Bode plots of plant, compensator and plant plus compensator are shown here. The plant is the RLC plant. As we already seen, the magnitude peaks at the resonant frequency, which is 1 over root LC. Before resonant frequency, the magnitude is 0 dB. After resonant frequency, it falls at 40 dB per decade because of the double pole omega square term in the denominator. Regarding the phase, before resonant frequency, the phase is 0 dB, and after at the resonant frequency, it changes from 0 to minus 180 degree. This is a compensator Bode plot. In the plant, at DC, the magnitude is 0 dB. So with this, the steady state error will be 50%. So we wanted to have an integrator at the origin. So that is given by this term in the transfer function of the compensator. So with this, the gain at the origin is infinity, similar to what we have seen in the PI controller. When the frequency crosses 778 radians per second, this term becomes more significant than this, and effectively these two terms will decide the magnitude, because all other frequencies are higher, so these all the terms will be 1. So S over 778 divided by S over 7780 will be 10. So at this point where a 0 starts, it become flat at magnitude is 10, that is equal to 20 dB here. After the first 0 here. Then we have second 0 somewhere here. It is at the resonant frequency here. That is this. So that gives additional 20 dB per decade. The magnitude increases. So because of this 20 dB per decade, which will be added to the RLC Bode magnitude, the 40 dB per decade will become 20 dB per decade, because this is a 20 dB per decade increasing, here 40 dB per decade decreasing, so net will be 40 dB per decade. That's why we are given a 0 here to reduce the slope when crosses 0. Then after this 0, then next pole comes, which will be magnitude will be falling at 20 dB per decade here. So the rising 20 dB per decade and falling 20 dB per decade here become flat. Then the last pole comes much after. It is not shown in the Bode plot. It is 100 kilohertz. This will be at 500 kilohertz. So then again it will be falling at 20 dB per decade after reaching this frequency. So this is the compensator whose transfer function is given here. So the open loop transfer function of the system is the plant plus compensator. So we need to add these two Bode plots. The magnitude plots of the plant and the compensator can be added. Even though magnitudes are multiplied, since it is represented in dB, which is proportional to log of magnitude, we can add these two magnitude plots to get the resultant open loop system transfer plot. Okay, so the magnitude is 0 dB until here. So when you add to this compensator magnitude, so net will be same as the compensator magnitude, because this is 0 here. So we have this up to this point, we have 20 dB here. So same thing. So here we are starting with 20 dB. So afterwards, the whole graph will be lifted by 20 dB. So whatever the 80 dB here will be 100 dB here, and then instead of falling at 40 dB per decade, it's going to fall at 20 dB per decade, because there is a pole at the resonant frequency. When this graph is lifted by 20 dB, here is 20 dB, and if you lift 20 dB here, the 0 crossing will happening at this frequency, that is 2 kilohertz. If the magnitude falls at 40 dB per decade, but because of the 0 here, the net magnitude is going to fall at 20 dB per decade. So the 0 crossing will be after 2 kilohertz. We can see in this plot, this is 0 dB. So 0 crossing here, 1, 2, 3, about 4 kilohertz is the 0 dB crossover frequency. And since the net magnitude plot is going to drop at 20 dB per decade because of 2 poles and 1 0. So it crosses the 0 dB at 20 dB per decade, which is a single pole. And there is another pole coming immediately after that. So that will give about 45 degree. So 90 degree minus about 45 degree minus is about 135 degree is the phase expected at this point. You can see here the phase is about around 40 degree here, this point. So we have a phase margin of about 40 degree, and the phase become 180 somewhere here, and then we have a very good gain margin of 30 dB. The control block diagram shown with the plan and the compensator. The compensator has been designed as explained in the previous slide, and this is the plant. Plant is nothing but RLC circuit, and this is a circuit used to simulate the controller, and this is the plant. This is a type 3 compensator. So this is the open loop Bode plot, nothing but the RLC circuit Bode plot here. So this is a magnitude, with compensator. So we have seen the, now we can see pole at the origin here. So also we can see the 20 dB in the flat region. The next two zeros are coming this area. So as soon as after the resonant frequency, you can see that 0 dB is here. The slope is here made it at 20 dB per decade. Then further increase in slope happens after crossing the 0 dB point. You can see that at 0 dB the phase is somewhere around 140. So we have 40 degree away from 180. So 40 degree phase margin. At 180 degree phase, the gain is somewhere around 30 minus 30 dB. So we have very good gain margin. It's more than 20 dB is very good, and any phase more than 40 is quite good. This is a simulated circuit. This is the op-amp. The op-amp has been modified so that it can drive the LCR circuit. Whatever the current required, it can provide that much current. And this LCR circuit, and then the output voltage divided by this network, and it's given to the type 3 compensator circuit. This is the reference at the non-inverting input. The feedback is coming at the inverting input. So the feedback voltage will be equal to the reference V in voltage at the steady state. These are simulation results. V in, this is the input voltage, is given with a ramp, slowly increase so that doesn't burden the actuator which is supplying the current to the RLC circuit. And this is the output voltage. You can see that output voltage, there is no steady state error, and it also follows the input voltage quickly without any oscillation, and almost within 9 milliseconds it settles. I have done a bad design to compare with the design we have been discussing so far. So this is the open loop Bode plot of this bad design. Earlier, we had a pole after the magnitude plot crossed the 0 dB after here. So the magnitude plot crossed the 0 dB at single slope or 20 dB per decade. So now I put this pole here, from here I shifted to resonant frequency. So now at the resonant frequency, after the resonant frequency rather, we have two poles of the plant RLC circuit, and one pole we just shifted from here to here, and 1 0 of the compensator. So 3 poles, 1 0, so net 2 poles, that is the magnitude will be falling at 40 dB per decade. We can see that the slope is 40 dB per decade here and continues to fall the same slope until the next frequency, next pole, which is after 100 kHz. Since it's crossing 0 dB with double pole at 40 dB per decade, we expect the phase to be close to 180 degree. So 0 dB crossover here, and then you can see the phase 180 degree, nearly 180 degree at that point. So we have very bad phase margin. So that reflects in the time domain waveform. This is a reference. This is the feedback supposed to follow the reference. You can see the oscillation, and that also it's increasing. The oscillation is increasing in magnitude. As expected, oscillations happen at the frequency at 0 dB crossover frequency. That is, here it is 2.3 kHz, and this oscillation frequency is also 2.3 kHz. This is the schematic of the compensator here. I made only one change. I made R3. Earlier it was 169. I made it to 1.5K. So RC value is increased and 1 over RC will be reduced. That is the pole, which will be from this frequency somewhere here, it reduced to near resonant frequency, that is 663 Hz. So we can now confidently say that the design process is fine. Your feedback to kannan@hesoft.in is very much appreciated.